In the 19th century, long before wireless communication, television signals, or modern technology filled the air around us, the world was already surrounded by invisible forces that no one could fully see or understand. A simple spark of electricity could jump between two metal surfaces. A magnet could pull iron toward it without any visible connection. Lightning could split the sky with sudden brightness and immense power. These phenomena were familiar, yet deeply mysterious. People could observe them, use them, and even harness them in limited ways. But the deeper question remained unanswered. What were these forces, and how did they truly move through space? At that time, electricity and magnetism were treated as separate subjects. Scientists studied them through experiments, carefully noting how electric charges behaved and how magnets interacted with metals. Some connections had already been discovered. It was known that electricity could create magnetism and that changing magnetic fields could produce electric currents. Yet these relationships were not fully understood. There was no single theory that explained them together as part of one unified system. Hidden within this confusion was a deeper structure waiting to be revealed. The person who would uncover that structure was James Clerk Maxwell, a quiet and thoughtful physicist whose ability to see patterns within complexity would transform the way humanity understands the physical world. James Clerk Maxwell was born in 1831 in Edinburgh, Scotland, into a family that valued curiosity, observation, and careful thinking. His father, John Clerk Maxwell, was not only well educated but also deeply interested in practical science and engineering. He encouraged young James to explore the world by asking questions and experimenting with ideas rather than simply accepting things as they appeared. Maxwell's early childhood was spent partly in the countryside at the family estate, a place filled with open land, natural textures, and quiet surroundings. This environment played an important role in shaping his thinking. Unlike crowded cities, the countryside offered space for slow observation. Maxwell would spend time examining patterns in nature, noticing how shapes formed, how light moved across surfaces, and how objects interacted with each other. From a very young age, he showed an unusual fascination with geometry and structure. He was not just interested in what things were, but in how they were arranged. He would draw shapes, trace curves, and think about how complex patterns could be described using simple rules. One of his early habits was stretching strings across objects to create geometric forms, exploring how shapes could be constructed and understood. This curiosity soon extended into more formal study. When Maxwell began school, his abilities quickly became clear, though his personality remained quiet and somewhat different from other students. He was deeply focused, often absorbed in his own thoughts, and more interested in understanding ideas than in social activity. Some classmates saw him as unusual, but his teachers recognized that his mind worked in a precise and creative way. At the age of 14, he produced his first scientific paper, a remarkable achievement for someone so young. In this work, he described a method for drawing oval curves using mathematical principles. What made this important was not just the result, but the way he approached the problem. He was already thinking about how physical shapes could be explained through mathematics, a theme that would define his later work. As he continued his education, Maxwell attended the University of Edinburgh, where he studied a wide range of subjects including mathematics, natural philosophy, and physics. He spent long hours reading, experimenting, and thinking about the laws that govern the natural world. Unlike many students who focused only on assigned material, Maxwell explored ideas deeply, often going beyond what was required. Later, he moved to the University of Cambridge, one of the leading centers of scientific thought at the time. Cambridge provided him with an environment where advanced mathematics and physics were studied at the highest level. There, Maxwell encountered the work of earlier scientists who had begun exploring the nature of forces. One of the most important influences on his thinking was Michael Faraday. Faraday had carried out a series of groundbreaking experiments showing that electricity and magnetism were closely related. He introduced the idea that space itself could contain invisible fields, regions where forces exist even without direct contact between objects. These fields could stretch through space, guiding the motion of particles and influencing physical behavior. Faraday's ideas were powerful, but they were mostly described in words and diagrams rather than precise mathematical language. Maxwell saw something more. He believed that these invisible fields could be described using equations. If the patterns behind electricity and magnetism could be expressed mathematically, then their behavior could be predicted with clarity and precision. This approach required a deep understanding of both physical intuition and advanced mathematics, something Maxwell uniquely possessed. Before fully focusing on electromagnetism, Maxwell explored several other areas of science. One of these was the study of color and light. He investigated how different colors combine and how the human eye perceives them. Through careful experimentation, he demonstrated that a wide range of colors could be created by combining just a few basic ones. This work even led to one of the earliest demonstrations of color photography, showing how red, green, and blue light could be used to recreate full color images. These studies were not separate from his later work. They reflected a consistent way of thinking. Maxwell was always searching for underlying patterns, simple principles that could explain complex phenomena. Whether studying light, color, or physical forces, he approached each problem with the same quiet determination to find structure within apparent complexity. As he continued his research, his attention increasingly turned toward the relationship between electricity and magnetism. Scientists already knew that an electric current could produce a magnetic effect, and that changing magnetic fields could generate electricity. Yet these ideas were still fragmented, lacking a unified explanation. Maxwell began to suspect that electricity and magnetism were not just connected, but were actually different aspects of the same fundamental force. To explore this idea, he started developing a system of equations that could describe how electric and magnetic fields behave, how they influence each other, and how they move through space. This work required not only mathematical skill, but also deep imagination, the ability to visualize invisible forces and express them in precise form. In quiet rooms filled with papers, calculations, and diagrams, Maxwell worked steadily, building a framework that would eventually unify electricity, magnetism, and light into a single theory. What he was beginning to uncover was far more than a simple connection between known phenomena. He was revealing that the space around us is not empty, but filled with dynamic fields that carry energy, interact with matter, and move in waves across the universe. And within this realization lay one of the most important discoveries in the history of science. As James Clerk Maxwell moved deeper into his study of electricity and magnetism, he entered a field that was already filled with important discoveries, yet still lacked a clear and unified explanation. Scientists like Michael Faraday had revealed that electric currents could create magnetic fields, and that changing magnetic fields could produce electric currents. These discoveries showed that electricity and magnetism were closely linked, but the connection between them remained incomplete. The ideas existed, but they were scattered, described through experiments and observations rather than brought together into a single, coherent system. Maxwell approached this problem in a very different way. Where Faraday had relied on physical intuition and experimental insight, Maxwell brought a mathematical perspective. He believed that if these invisible forces truly followed consistent laws, then those laws could be expressed through equations. Mathematics, to him, was not just a tool for calculation, but a language capable of describing the deepest structures of nature. He began by carefully studying everything that had already been discovered. He examined Faraday's concept of lines of force, which describe how electric and magnetic influences extend through space. These lines were not physical objects, but they represented the direction and strength of forces at different points. Faraday imagined space as filled with these invisible patterns, almost like a fabric through which forces could move. Maxwell took this idea seriously. Instead of treating space as empty, he began thinking of it as something active, filled with fields that could store and transfer energy. This was a major shift in understanding. If fields were real, then their behavior could be studied, measured, and described mathematically. The challenge was to translate Faraday's visual and experimental ideas into precise equations. This task required years of work. Maxwell developed a set of mathematical relationships that describe how electric fields are created by charges, how magnetic fields are produced by moving charges, and how these fields change over time. Each equation captured a different aspect of the interaction between electricity and magnetism, but together they formed a unified system. One of his key insights involved the behavior of changing electric fields. Scientists already knew that a changing magnetic field could produce an electric current. This was the principle behind electromagnetic induction, discovered by Faraday. But Maxwell realized that the reverse must also be true in a deeper sense. If a changing magnetic field can create an electric field, then a changing electric field should also be able to create a magnetic field, even in empty space where no physical current is flowing. This idea was not obvious at the time. In traditional thinking, magnetic fields were always linked to physical currents, such as electrons moving through a wire. Maxwell proposed something more subtle. He introduced the concept of what he called displacement current, a term used to describe how a changing electric field could act like a current, generating a magnetic field even without the movement of charged particles. This was a crucial step. By adding this idea to his equations, Maxwell completed the symmetry between electricity and magnetism. Electric fields could create magnetic fields, and magnetic fields could create electric fields. The two were no longer separate phenomena, but deeply interconnected aspects of a single system. Once this connection was fully expressed, something extraordinary emerged from the mathematics. Maxwell's equations suggested that changes in electric and magnetic fields could travel through space as waves. These waves did not require a material medium like sound waves traveling through air. Instead, they could move through empty space itself, carried by the interaction between electric and magnetic fields. As one field changed, it would generate the other, and this continuous interaction would allow the disturbance to move forward. Maxwell calculated the speed at which these waves would travel. When he worked through the equations, he found a value that was strikingly familiar. The speed of these electromagnetic waves was the same as the measured speed of light. This result was not a coincidence. It led Maxwell to a bold and revolutionary conclusion. Light itself is an electromagnetic wave. What people see as light, what allows us to perceive the world around us, is actually a form of energy traveling through space as oscillating electric and magnetic fields. This idea connected two areas of science that had previously been studied separately. Optics, the study of light, and electromagnetism, the study of electric and magnetic forces, were now part of the same unified theory. The implications of this discovery were enormous. It meant that light did not require a mysterious substance or medium to travel through space. It could move through the vacuum of space, carrying energy across vast distances. It also suggested that there might be other types of electromagnetic waves beyond visible light, waves that humans could not see but that followed the same principles. At the time, these predictions went far beyond what could be directly observed. Maxwell himself never saw electromagnetic waves beyond visible light. The technology to detect such waves did not yet exist. Yet his equations clearly indicated that they should be there, waiting to be discovered. Despite the power of his ideas, not everyone immediately accepted them. Maxwell's work was highly mathematical, and many scientists of the time found it difficult to understand. Faraday's intuitive descriptions were easier to visualize, while Maxwell's equations required deep mathematical knowledge. As a result, his theory spread slowly at first, appreciated mainly by a smaller group of physicists who could follow his reasoning. Even so, the structure he had built was solid. His equations did not just describe known phenomena. They predicted entirely new ones. They showed that electricity, magnetism, and light were all part of a single unified framework governed by the same underlying laws. In quiet calculations and careful reasoning, Maxwell had transformed invisible forces into something understandable. revealing that the space around us is alive with energy, constantly shaped by fields moving and interacting in ways that extend far beyond what the human eye can see. As James Clerk Maxwell's theory of electromagnetism began to take shape, its full significance was not immediately understood. His equations were powerful, elegant, and deeply unifying, yet they were also complex and difficult for many scientists of the time to follow. Unlike experimental discoveries that could be directly observed in a laboratory, Maxwell's work existed largely in the realm of mathematics. It described a reality that could not yet be fully seen, only predicted through careful reasoning. Still, within those equations lay one of the most important predictions in the history of science. Maxwell had shown that electric and magnetic fields could move through space as waves, and that these waves traveled at the same speed as light. From this, he concluded that light itself was an electromagnetic wave. But the equations suggested something even more profound. If visible light was one form of electromagnetic radiation, then there must be many other forms as well, waves with different wavelengths and frequencies that existed beyond the limits of human vision. At the time, this idea was extraordinary. The human eye can only detect a very small portion of the electromagnetic spectrum. Maxwell's theory implied that beyond the colors we can see, there were invisible waves filling space, moving constantly, carrying energy in ways no one had yet directly observed. These waves could be longer or shorter than visible light, slower or faster in their oscillations, yet all governed by the same fundamental laws. Maxwell did not live to see these predictions confirmed. In the years following his work, scientists began exploring the implications of his theory more deeply. One of the most important figures in this effort was the German physicist Heinrich Hertz. In the late 19th century, Hertz designed experiments to test whether electromagnetic waves beyond visible light truly existed. Using carefully constructed and electrical circuits, Hertz was able to generate and detect waves that behaved exactly as Maxwell's equations had predicted. These waves could travel through space, reflect off surfaces, and interfere with each other, just like light. Hertz had successfully demonstrated the existence of radio waves, a form of electromagnetic radiation that lies beyond the visible spectrum. This was a turning point. For the first time, Maxwell's abstract mathematical predictions had been confirmed through direct experiment. The invisible waves he had described were real. They could be created, detected, and studied in a laboratory. This discovery opened the door to entirely new forms of technology. In the years that followed, scientists and engineers began exploring practical uses for electromagnetic waves. Guglielmo Marconi developed wireless communication systems that could send signals through the air using radio waves. What had once been an invisible and theoretical concept became the foundation for radio transmission, allowing messages to travel across long distances without wires. This development marked the beginning of a new era. Communication was no longer limited to physical connections. Information could now move through space itself, carried by the electromagnetic waves that Maxwell had predicted. Over time, this technology expanded into many forms, including television, radar, and eventually modern wireless communication systems that connect people across the world. Maxwell's work also had a profound influence on the development of modern physics. His equations introduced the idea that fields, rather than just particles, play a fundamental role in the structure of the universe. Instead of thinking of forces as direct interactions between objects, scientists began to understand that space itself could carry energy and influence motion through fields. This concept became central not only to electromagnetism, but also to later theories in physics. In the early 20th century, Albert Einstein would build upon these ideas while developing the theory of relativity. Maxwell's equations showed that the speed of light is constant, a fact that played a crucial role in Einstein's understanding of space and time. The realization that the speed of light does not change, regardless of the observer's motion, challenged traditional ideas and led to a completely new way of thinking about the universe. In this way, Maxwell's work extended far beyond electricity and magnetism. It helped reshape the foundations of physics itself, Despite the importance of his discoveries, Maxwell remained a modest and thoughtful individual. He was known for his quiet personality and his deep focus on understanding rather than recognition. Throughout his life, he continued exploring a wide range of scientific topics, from the behavior of gases to the nature of Saturn's rings, which he studied using mathematical analysis. His work on Saturn revealed that the rings could not be solid structures, but must instead be composed of countless small particles orbiting the planet. This conclusion, reached through mathematical reasoning, was later confirmed by observation, demonstrating once again his ability to uncover hidden truths through careful analysis. Maxwell also contributed to the study of thermodynamics and statistical mechanics, helping to explain how the behavior of large numbers of particles gives rise to the properties of gases. These contributions further demonstrated his ability to connect mathematics with physical reality. Throughout his career, Maxwell showed a consistent way of thinking. He looked beyond surface appearances, searching for underlying patterns that could explain complex systems. Whether studying light, electricity, or the motion of particles, he approached each problem with patience and precision, building a deeper understanding step by step. By the time his work on electromagnetism was fully appreciated, it had already begun transforming science and technology. The invisible waves he had predicted were now being used to communicate, explore, and understand the world in entirely new ways. What had once existed only as equations on paper was becoming a fundamental part of everyday life. As the 19th century moved toward its later years, the true impact of James Clerk Maxwell's work began to unfold more clearly. What he had developed through careful reasoning and mathematical precision was not just a theory about electricity and magnetism, but a complete framework that described how energy moves through space. His equations revealed that the universe is filled with fields, invisible yet real, constantly interacting, carrying energy, and shaping the behavior of matter in ways that extend far beyond what human senses can directly perceive. During his lifetime, however, Maxwell did not experience the full recognition that his work would later receive. His ideas were respected among a smaller circle of physicists, but the depth of his contribution was not immediately understood by the wider scientific community. Part of this was due to the nature of his work itself. His theory was expressed through advanced mathematics, requiring a level of abstraction that made it difficult for many to grasp. Unlike experimental demonstrations that could be easily seen and repeated, Maxwell's equations described a hidden structure of reality that required imagination as well as calculation to fully appreciate. Even so, his influence continued to grow quietly. Maxwell spent part of his later career as a professor at King's College London, where he worked on developing and refining his theory of electromagnetism. It was during this period that he published his most important work, a treatise on electricity and magnetism. This book brought together his ideas in a detailed and systematic form, presenting the equations and concepts that would later become the foundation of modern electromagnetic theory. The treatise was not easy reading. It required deep concentration and a strong background in mathematics, but for those who studied it carefully, it revealed a new way of understanding the physical world. It showed that electricity, magnetism, and light were not separate phenomena, but different expressions of the same underlying reality. This unification was one of the greatest achievements in the history of science, comparable to Newton's earlier unification of motion and gravity. In the later years of his life, Maxwell returned to Cambridge, where he became the first Cavendish Professor of Physics. In this role, he helped establish the Cavendish Laboratory, which would go on to become one of the most important centers of scientific research in the world. Under his guidance, the laboratory was designed as a place where experimental and theoretical physics could work together, reflecting his belief that understanding comes from the combination of observation and mathematical reasoning. Despite his achievements, Maxwell's life was relatively short. He died in 1879 at the age of 48. At the time of his death, many of the implications of his work were still unfolding. The experimental confirmation of electromagnetic waves by Heinrich Hertz would come only a few years later, and the technological revolution built upon those discoveries would take decades to fully develop. Yet, even without witnessing these developments, Maxwell had already changed the course of science. In the years that followed, his equations became central to physics. They were refined and expressed in more compact forms, but their core meaning remained the same. They describe how electric and magnetic fields are generated, how they interact, and how they propagate through space as waves. These ideas became the foundation for a vast range of technologies. Radio communication, which allows signals to travel across continents, relies directly on electromagnetic waves. Radar systems, used for navigation and detection, are based on the reflection of these waves. Television and wireless communication systems transmit information through variations in electromagnetic signals. Even the devices used to access modern digital networks depend on principles that trace back to Maxwell's theory. Beyond technology, his work also shaped the direction of theoretical physics. Maxwell's equations introduced the idea that fields are fundamental components of reality. This concept influenced the development of later theories, including Einstein's work on relativity. The constant speed of light, predicted by Maxwell's equations, became a central principle in understanding space and time. It led to the realization that measurements of distance and duration are not absolute, but depend on the observer's motion. In this way, Maxwell's work helped bridge the gap between classical physics and the modern understanding of the universe. What began as an attempt to understand electricity and magnetism evolved into a theory that connected light, energy, and the structure of space itself. It revealed that the universe is not made only of matter, but also of fields that carry energy and information across vast distances. Today, Maxwell is remembered as one of the greatest physicists in history. His equations are still taught to students around the world, forming a core part of scientific education. They are used to design technologies, explore space, and study the fundamental behavior of the universe. The invisible waves he described now carry voices, images, and data across the globe, connecting people in ways that would have been unimaginable in his time. James Clerk Maxwell's life shows how powerful ideas can emerge from quiet thought and careful reasoning. Without large instruments or dramatic experiments, he uncovered the hidden structure of forces that surround us every moment. He revealed that light, electricity, and magnetism are all part of a single, unified system governed by precise and elegant laws. Through his work, the invisible became understandable, and the empty space around us was revealed to be filled with energy, motion, and connection, shaping the world in ways that continue to influence every part of modern life.